At the end of the 19th century, the world of physics stood tall and confident, almost proud of the vast intellectual empire it had constructed. Scientists believed they had uncovered nearly all the important laws governing nature. Gravity, electricity, magnetism, heat, and motion, everything seemed to fit into the clear and predictable rules set by classical physics. Students in universities were sometimes advised not to study physics because, according to some professors, there was nothing major left to discover. Yet beneath this surface of certainty, a quiet storm was forming, a storm that would be sparked by a soft-spoken German physicist named Max Planck, a man who never imagined he would turn the world upside down. Planck did not enter physics with rebellion in his mind. Born in 158 in Kiel, Germany, he was raised in a family that valued scholarship, order, and tradition. His upbringing shaped his character, disciplined, rigorous, and grounded. He admired the beauty of mathematics and the harmony of the physical world, and he believed deeply in the idea that nature could be fully described by elegant laws. But nature had other plans. It would present him with a problem that resisted elegance, a problem that seemed to defy the very foundations of classical thought. And Planck, driven by scientific honesty rather than ambition, would pursue it until he stumbled upon an idea so revolutionary that even he hesitated to believe it. The problem was known as the Blackbody radiation problem. A blackbody is an idealized object that absorbs all radiation falling on it and emits light depending only on its temperature. For decades, physicists attempted to calculate the exact distribution of light emitted at different wavelengths. When experimentalists heated metals in furnaces and observed the glow, from dull red to bright white, they were seeing blackbody radiation in action. But the theories of the time failed miserably. Classical physics predicted something absurd. As wavelength decreased, the emitted radiation should increase without limit, shooting off to infinity. This prediction became known as the ultraviolet catastrophe, a dramatic name that reflected how catastrophic it was to established physics. Something fundamental was clearly wrong. Planck felt compelled to solve the problem not because he expected glory, but because the inconsistency deeply bothered him. His scientific philosophy was built on the belief that nature must make sense. Yet here was a part of nature that refused to obey the rules. In his quiet office in Berlin, Planck worked tirelessly, trying one approach after another, adjusting assumptions, refining calculations, and searching for a formula that matched the experimental data. What he needed was not a new philosophy, but a new mathematical expression. At least, that is what he believed. One crisp evening in 1900, after months of frustration, Planck finally found a formula that reproduced the blackbody curve perfectly. But the success came with a price he did not fully understand at first. To arrive at the correct formula, he had to make a mathematical assumption that energy was not emitted in a smooth and continuous flow. Instead, it came in little, discrete bundles, like tiny packets. He called these packets energy elements, later known as quanta. It was a desperate assumption, something he introduced reluctantly as a last resort. But the universe does not bend to human preferences, and the math was unyielding. The only way to match the data was to accept that energy behaved in a fundamentally different way than anyone had ever imagined. This was the birth of the quantum idea, a moment that would later be compared to the revolution brought by Copernicus centuries earlier. But at the time, Planck had no desire to overthrow classical physics. He considered his discovery a temporary fix, a mathematical trick that would someday be explained by conventional reasoning. Yet even as he downplayed the significance, something extraordinary had happened. A new door had opened, one that would lead humanity into an entirely new world. To derive his formula, Planck introduced a new constant, a number that would soon become one of the most important constants in all of science, Planck's constant, symbolized as h. Though the number itself was tiny, its meaning was enormous. It implied that energy was fundamentally granular, not smooth. This ran counter to everything physicists believed. They thought light was a wave, continuous and flowing. But Planck's constant suggested a hidden structure in energy itself, a structure no one had ever seen. When Planck presented his formula on December 14, 1900, at a meeting of the German Physical Society, very few people realized the magnitude of what he had done. The atmosphere was calm, the audience polite, the event ordinary. There were no gasps of shock, no headlines in newspapers, no immediate philosophical debates. But history would look back at that meeting as the moment quantum theory was born, the moment modern physics began. In that quiet lecture hall, a new chapter of human understanding started to unfold. Planck, however, remained cautious. He was not eager to embrace the radical implication that energy was quantized. He had always admired the continuity of classical physics, the smooth curves, the predictable patterns. Waves were waves, not packets. Energy was energy, not chunks. And yet the data did not care about his preferences. Nature had spoken, and it had spoken through the mathematics he had trusted all his life. Over time, as other scientists re-examined his work, they realized that his assumption was not just a clever trick. It was a window into a deeper truth. It would take another great mind, Albert Einstein, to recognize the true significance of what Planck had proposed. In 1905, Einstein expanded Planck's idea and applied it to light itself, suggesting that light comes in packets called photons. This was far more radical than Planck had intended, and at first Planck did not agree. But Einstein saw what Planck could not yet accept. The quantum idea was not just a mathematical workaround. It was a fundamental feature of the universe. Planck's reluctant step into the quantum realm marked the beginning of a scientific revolution that would reshape our understanding of atoms, energy, and the very fabric of reality. It challenged the comforting predictability of classical physics and replaced it with a world full of probabilities, uncertainties, and unimaginable possibilities. Yet behind this revolution was a man who sought nothing but truth. He did not aim to rewrite the laws of physics. He only aimed to solve a stubborn problem. In doing so, he changed everything. The introduction of the quantum idea in 1900 was not the loud arrival of a new era, but a gentle whisper. It was not accompanied by fireworks, but by quiet calculations scribbled in notebooks and the soft turning of paper in candle-lit rooms. The significance of this idea grew slowly. Year after year, experiment after experiment, the quantum nature of reality revealed itself more clearly. Atoms behaved like tiny storms of probability. Electrons jumped between orbits without passing through the space in between. Waves behaved like particles, and particles behaved like waves. Every discovery traced its roots back to that night in 1900, when Max Planck made the choice to follow truth, even when it led him into unfamiliar territory. Planck himself later reflected on the moment with humility, noting that he had been forced into his discovery by nature's refusal to conform to classical expectations. He once said, "I did not seek the quantum, it sought me." This statement captures the essence of his journey. He had no intention of becoming a revolutionary, yet he became the father of quantum theory simply by refusing to look away from the contradiction in front of him. The quantum idea began as a solution to a small theoretical problem, but soon grew into the backbone of the entire landscape of modern physics. Technologies like lasers, semiconductors, computers, and MRI machines can all trace their origins back to Planck's constant, that tiny number that quietly governs the behavior of the microscopic world. Without quantum theory, the digital age would not exist, and without Max Planck's courage to introduce the quantum idea, the theory might never have emerged. To understand the weight of his contribution, one must imagine the intellectual climate of the time. Classical physics was not just a theory, it was a world view. It described the universe as a giant machine, predictable and orderly. Every event had a cause, every motion could be calculated. And then came quantum theory, suggesting that the universe, at its deepest levels, was not entirely predictable, but instead governed by probabilities. It was a shift so profound that it changed not only science, but also philosophy, art, and human imagination. Planck, however, remained a man of classical temperament. Even after the quantum revolution unfolded, he continued to believe in a deeper underlying order, a harmony that perhaps lay beyond human understanding. He respected the new physics, but never sought to dismantle the old. Instead, he became the bridge between two worlds, the world of classical certainty and the world of quantum mystery. The significance of Planck introducing the quantum idea in 1900 lies not only in the scientific implications, but also in the human story behind it. It is a story of persistence, humility, and intellectual honesty. It reminds us that breakthroughs often come from unlikely places, and that the greatest discoveries sometimes emerge from the quiet dedication of individuals who simply refuse to ignore the truth. As the 20th century progressed, the quantum idea blossomed into a vast field of research. Generations of scientists built upon Planck's foundation, exploring the strange and beautiful behavior of particles, fields, and energy. Quantum mechanics became one of the most successful theories ever created, explaining phenomena with astonishing precision. Yet no matter how complex the theory became, it always traced back to Planck's original insight. In the end, the story of Max Planck introducing the quantum idea in 1900 is not just a story of physics, but a story of the human quest for understanding. It is a testament to the power of curiosity, the importance of integrity, and the courage required to challenge old beliefs. It shows how one unexpected insight can transform our perception of the universe and open doors to realms we once believed impossible to reach. The legacy of that moment continues to shape our world today, more than a century later. Every smartphone, every laser beam, every digital device carries within it the whisper of Planck's constant. Every experiment in quantum computing, every exploration of the atomic world, every attempt to unify physics owes something to the quiet figure who, in the year 1900, followed the logic of nature to its surprising conclusion. And so the quantum revolution began not with a shout, but with the soft voice of Max Planck, introducing an idea that would illuminate the universe in ways humanity had never imagined. As the 20th century began to unfold, Max Planck's quantum idea quietly moved through the scientific world like a faint tremor before an earthquake. At first, it attracted little attention, but for those who examined it closely, something unsettling yet fascinating began to emerge. The simplicity of the idea, a discrete packet of energy proportional to frequency, carried consequences far greater than Planck himself imagined. It was as if a small crack had appeared in the wall of classical physics, and through that crack, an entirely new universe could be glimpsed. This universe did not operate smoothly like the gears of a mechanical clock. Instead, it flickered with jumps, probabilities, and strange dualities. The seeds of this new universe had been planted in 1900, but it would take decades for scientists to fully explore the vast intellectual landscape that Planck had unknowingly opened. Einstein was the first to walk boldly through the doorway. When he examined Planck's formula, he saw something deeper than Planck was willing to accept. Einstein realized that the idea of discrete packets was not just a mathematical trick. It was a statement about the actual physical nature of light. In 1905, he proposed that light itself was composed of tiny particles, later named photons. This was an astonishing claim. The physics community had fought long and hard to establish that light was a wave. Waves could interfere, blend, and behave continuously. But if light was made of particles, how could it also form interference patterns? The contradiction seemed impossible. Still, Einstein persisted, and the evidence supported him. Planck initially resisted Einstein's interpretation. It felt too radical, too disruptive to the order he cherished. Yet even he could not deny that Einstein's approach explained the photoelectric effect, a phenomenon where light striking a metal surface ejects electrons, in a way that classical physics could not. The unthinkable was happening. Light, the most familiar thing in nature, behaved both as a wave and as a particle. Reality was beginning to show a dual face, and Planck's quantum had opened the door to this new understanding. As the years passed, more discoveries began to stack upon one another like puzzle pieces that refused to fit into the classical framework. Scientists studying the inner structure of atoms discovered that electrons did not orbit the nucleus like planets orbiting the Sun. Instead, they occupied discrete energy levels. This strange behavior aligned perfectly with the quantum idea. Niels Bohr, a young Danish physicist, used Planck's quantum assumption to build a model of the atom that could explain why atoms emitted light at specific frequencies. Atoms, he argued, absorbed or released quanta of energy when electrons jumped between fixed energy levels. The elegant simplicity of this explanation carried enormous power. Suddenly, atomic spectra, once mysterious patterns of light, were nothing more than the visible signature of quantum jumps. The scientific world began to realize that Planck's idea was not an isolated trick, but the foundation of a vast and growing theory. The quantum seemed to be woven into the very fabric of nature. Still, many resisted the implications. The classical world view was deeply cherished. It promised certainty, determinism, and predictability. The quantum idea, on the other hand, suggested randomness and discontinuity. It claimed that reality at the smallest scales did not unfold smoothly, but in abrupt, unpredictable leaps. This new philosophy of nature stunned even Planck. Though he accepted the necessity of the quantum idea, he never fully embraced the philosophical implications. He was a man grounded in the old world, yet he had given birth to a new one. This role was both inspiring and unsettling for him. While younger physicists celebrated the strange possibilities of quantum theory, Planck remained cautious, forever tied to the classical ideals that had shaped his early thinking. By the 1920s, the quantum revolution had gained unstoppable momentum. New mathematical tools were needed to describe the bizarre behavior of electrons and light. Out of this need came two monumental formulations of quantum mechanics: Heisenberg's matrix mechanics and Schrödinger's wave mechanics. Though very different in approach, both described the same underlying reality, a reality Planck's quantum idea had revealed. The idea that energy came in discrete packets had grown into a full-fledged theory predicting how particles moved, interacted, and existed. It was as though Planck had planted a single seed, and from that seed an immense forest had flourished. In this forest, many strange and counterintuitive ideas lived. One was the concept of wave, particle duality. Every particle had both a wave nature and a particle nature. Another was the uncertainty principle, which stated that certain pairs of properties, such as position and momentum, could never both be known with perfect accuracy. These concepts were not philosophical guesses. They were mathematical necessities of the quantum world. Reality, it turned out, did not behave like the calm, predictable mechanisms of classical physics. Instead, it pulsed with probabilities, possibilities, and inherent limits on what could be known. All of this traced back to the year 1900, when Max Planck had taken a bold and reluctant step into the unknown. His introduction of the quantum idea was now recognized as the pivotal moment that separated classical physics from the modern age. But while the scientific community was growing more comfortable with the implications of quantum mechanics, Planck himself continued to grapple with the philosophical consequences. He accepted the mathematics and the empirical success, yet he always believed that beneath the seeming randomness there must be some deeper order, a structure not yet understood. As quantum theory grew, its practical impact began to transform the world. The technologies that emerged from this theory were nothing short of revolutionary. The understanding of electron behavior in solids led to the invention of semiconductors, which became the foundation of the entire computer industry. Lasers, which operate using quantum principles, became essential in medicine, communications, and manufacturing. MRI machines, electron microscopes, solar cells, and countless modern technologies owe their existence to the quantum idea. The world was reshaped not only intellectually but physically through devices and tools that could not have been created without Planck's constant and the laws that followed from it. The significance of Planck's discovery becomes clearer when one considers how profoundly quantum theory has influenced our daily lives. Every email sent, every digital photograph taken, every GPS signal received, these are all the gifts of a theory born from a single reluctant assumption. Without the quantum idea, modern society would look drastically different, perhaps unrecognizable. Yet Planck himself never imagined such consequences. He was a theorist, driven not by ambition for technological revolution, but by curiosity and a commitment to resolving a stubborn contradiction. History often remembers great scientific revolutions as the work of bold idealists, but Planck's story is subtly different. His revolution was born not from a desire to challenge the establishment, but from a determination to preserve scientific truth. It is ironic that a man who valued classical physics so deeply became the founder of the theory that dismantled it. But perhaps this is precisely why his discovery remains so compelling. Planck did not seek to rewrite the rules of nature. He simply followed the evidence. And in doing so, he opened a path toward an understanding of the universe far beyond what anyone at the time could imagine. The quantum idea, introduced by Planck in 1900, also reshaped the philosophy of science. Classical physics had encouraged a deterministic world, in which every event had a cause, and the future could be predicted precisely if all initial conditions were known. Quantum mechanics challenged this certainty by introducing fundamental limits and probabilistic outcomes. This shift sparked debates not only in physics but in philosophy, as thinkers grappled with the implications of a universe where uncertainty was not a sign of ignorance but a built-in feature of reality. Planck's work forced humanity to confront the possibility that the world was more mysterious, more complex, and more dynamic than classical physics had led us to believe. Despite his cautious nature, Planck lived long enough to see the quantum theory he initiated become one of the pillars of modern science. He watched as young physicists pushed its boundaries, exploring strange new phenomena like quantum tunneling, entanglement, and superposition. Each discovery confirmed that the universe behaved in ways far stranger than classical physicists had ever allowed themselves to imagine. For all his reluctance, Planck became a respected elder statesman of the new quantum world. As he grew older, Planck continued to reflect on the path that had led him to his discovery. He often spoke of the moment he introduced the quantum assumption as a step he was forced to take by nature herself. He did not view himself as a revolutionary, but as a servant of truth. He believed that science required a willingness to follow reality wherever it led, even if it disrupted long-held beliefs. This humility and dedication are perhaps the most striking aspects of his legacy. He changed the world not by seeking fame, but by seeking understanding. The influence of Planck's quantum idea continues to expand even today. In the 21st century, scientists explore quantum computing, a field that promises to harness quantum behavior to perform calculations far beyond the reach of classical computers. Quantum communication seeks to use entanglement to create secure channels of information. Quantum biology investigates the role of quantum effects in living organisms. Each new frontier traces its lineage back to the moment Planck introduced his constant and proposed that energy came in discrete quanta. What began as a small detour from classical theory now shapes the future of technology, research, and human progress. The story of Planck's quantum idea is not just the story of a scientific discovery, but of the unfolding of human knowledge. It teaches us that the universe often reveals its secrets slowly, through the patient work of those willing to question assumptions. It shows how truth can emerge from unexpected places, and how a single insight can echo across centuries. Planck's quantum idea serves as a reminder that intellectual breakthroughs often begin with questions that seem small or obscure. But within those questions lies the potential to transform not only science, but the entire human experience. Looking back, it is astonishing to think that a problem as specific as Blackbody radiation could lead to such profound consequences. Yet this is the nature of scientific exploration. The universe hides its mysteries in the details, and it rewards those who pursue them with persistence. Planck's willingness to confront inconsistency, to question the foundations of physics, and to propose an idea that risked ridicule reveals the courage that lies at the heart of scientific discovery. He showed that progress requires both boldness and humility, the boldness to propose new ideas and the humility to accept when old ones fail. In the final years of his life, Planck's scientific contributions were celebrated around the world. He received the Nobel Prize, countless honors, and the admiration of generations of scientists. But the true measure of his impact lies not in awards, but in the enduring power of the quantum theory he founded. His work stands as one of the most significant turning points in the history of science, comparable to the revolutions of Copernicus, Newton, and Darwin. Through his quiet dedication, Max Planck helped humanity take a monumental step toward understanding the nature of reality itself. The quantum idea he introduced in 1900 continues to resonate across physics, philosophy, technology, and human imagination. It tells us that the universe is far stranger and more beautiful than classical physics ever allowed. It tells us that even the most unlikely ideas can reshape the world, and it reminds us that the pursuit of truth, honest, careful, and persistent, can lead to discoveries that transcend generations. Max Planck did not intend to transform the world. Yet by following the evidence, he opened the door to the quantum age, forever changing our understanding of energy, light, and the fundamental workings of the cosmos. At the turn of the 20th century, physics appeared to stand on solid ground. Its greatest minds believed they had unlocked the major secrets of nature. Mechanisms of motion, thermodynamics, electromagnetism, and the behavior of matter all seemed to fall cleanly into the laws defined by Newton, Maxwell, and Boltzmann. Yet behind this confidence was a small, persistent problem, one that seemed trivial at first, but grew more troubling the deeper scientists explored it. This problem concerned the nature of thermal radiation, the glow an object gives off when heated. It was known as Blackbody radiation. Simple in description, stubborn in behavior, it defied prediction and threatened to expose cracks in the very structure of classical physics. And it was Max Planck, through relentless persistence rather than revolutionary intention, who finally solved it. Blackbody radiation was more than an academic curiosity. It represented a fundamental question: how does energy behave when emitted as light by a heated object? When a piece of iron is heated until it glows red, or when a furnace radiates a bright orange glow, that light follows specific patterns based on temperature. Physicists wanted to predict these patterns mathematically. They wanted a formula that described how much light should be emitted at each wavelength. Such a formula would bridge theory and experiment, uniting the physics of heat and the physics of light. For decades, scientists attempted to build that bridge. They used the accepted rules of classical physics to predict the intensity of radiation as a function of wavelength. At long wavelengths, their predictions matched experiments well, but as they moved toward shorter wavelengths, the ultraviolet region, the formulas exploded into nonsense. The predicted intensity shot up to infinity. This was absurd. No furnace ever blasted infinite energy. No object ever produced an uncontrollable spike in ultraviolet radiation. The experimental data showed a neat curve, rising, peaking, then falling. But classical physics predicted a catastrophe, a runaway infinity at the short wavelength end of the spectrum. This conflict became known as the ultraviolet catastrophe, a term that reveals both the problem and the looming crisis it represented. Nature was behaving one way, but the equations said it should behave another. It was not simply a matter of refining measurements or adjusting numbers. Something was fundamentally wrong with the logic of the theory itself. And this frightened physicists. If classical theory could not explain something as basic as the glow of a heated object, then perhaps its entire foundation needed to be questioned. Max Planck found himself drawn to this problem, not because he sought fame or disruption, but because he was a man who believed deeply in the harmony of physical laws. He was motivated by a desire for intellectual unity, a desire to see nature's behavior expressed through elegant mathematics. The Blackbody radiation problem, with its resistance to theoretical explanation, disturbed him. He felt compelled to solve it, to mend the cracks that threatened the beautiful structure of classical physics. To Planck, this was not an opportunity for revolution, but a duty to restore order. Throughout the 1890s, he struggled with the problem, trying one theoretical approach after another. His colleagues, such as Ludwig Boltzmann, had made significant progress using statistical methods, but Planck was hesitant to embrace Boltzmann's probabilistic view of entropy. Still, as the Blackbody puzzle deepened, Planck began to reconsider. He realized that the traditional deterministic methods of classical physics offered no path forward. The ultraviolet catastrophe was not a minor error. It was a fundamental contradiction. Something had to change. Planck approached the problem with discipline and desperation. He analyzed experimental measurements from the Kaiser Wilhelm Institute, pored over data curves, and tried to find a mathematical form that could match the observed radiation spectrum. The formulas proposed by Wilhelm Wien had come close but failed at longer wavelengths. The Rayleigh-Jeans law, derived from classical assumptions, worked for long wavelengths but exploded at short ones. It was as though every theory managed to describe part of the curve, but none could unify the whole. Planck wanted unity. He wanted a single formula that worked everywhere. In 1900, after intense effort, Planck discovered a mathematical expression that matched the experimental data perfectly. It reproduced the rise, the peak, and the decline of the radiation curve. It was elegant and accurate. For the first time, a single formula could describe the spectrum of Blackbody radiation across all wavelengths. But this success came at a cost. To derive the formula, Planck had to make a bold and deeply unsettling assumption. He had to assume that energy was not exchanged continuously between matter and radiation, as classical physics insisted. Instead, it came in discrete packets, tiny chunks of energy proportional to the frequency of the radiation. Planck introduced a constant, h, which represented the size of these energy packets. This constant was unbelievably small, so small that its significance might easily have been overlooked. But its meaning was enormous. Energy was quantized. Nature did not allow arbitrary, continuous amounts of energy. It operated in steps, in jumps, in quanta. Planck was shocked by the implications. He had always been a defender of classical physics. And yet, here he was, proposing a concept that broke it. But Planck's priority was truth, not comfort. He submitted his idea because it worked, because it matched the data, solved the ultraviolet catastrophe, and agreed with every experiment. He presented his findings on December 14, 1900, to the German Physical Society. It was a quiet moment without fanfare, but history would later mark it as the turning point, the birth of quantum theory. Planck's solution to the Blackbody radiation problem was not recognized immediately as a revolution. Even Planck himself hesitated to embrace its deeper consequences. He viewed his quantization of energy as a mathematical trick rather than a radical restructuring of physical law. But the seeds had been planted. Other scientists soon realized that Planck's idea was more than a convenient fix. It was a window into a new understanding of reality. The Blackbody radiation problem had forced Planck into unfamiliar territory, but it also opened pathways that classical physics had kept locked. It turned out that the glow of a heated object was a clue to the underlying architecture of nature. In solving this one problem, Planck did far more than create a formula. He revealed that at the smallest scales, the world did not behave like a smooth, continuous machine. It behaved in discrete, quantized steps. Light did not flow like a wave alone. It arrived in packets. Matter did not exchange energy gradually. It did so in jumps. Planck had solved a practical physics problem, but the implications touched something deeper. His assumption was the first crack in the classical worldview, the first hint that something beyond Newton and Maxwell was waiting to be discovered. The Blackbody radiation curve, once an obscure graph in experimental physics, became the birthplace of quantum mechanics. Planck's work suggested that matter and energy were governed by laws far stranger than classical physics had ever imagined. It implied a universe woven not from continuous threads, but from discrete building blocks. Though Planck did not fully accept this at first, his work laid the foundation for the scientists who would come after him. Einstein soon used Planck's quanta to explain the photoelectric effect, and later Bohr used them to describe the structure of the atom. Schrödinger, Heisenberg, and Dirac expanded these ideas into the full framework of quantum mechanics. All of them traced their work back to Planck's solution to the Blackbody radiation problem. The problem itself, once considered a minor inconsistency, became the doorway into the atomic world. It showed that even the most ordinary phenomenon, a glowing object, could hold secrets about the deepest levels of reality. Planck's willingness to confront the contradiction and follow the mathematics wherever it led allowed him to expose the limits of classical physics and open the path to a new understanding of nature. His solution was not just a scientific achievement. It was a moment of profound philosophical transformation. It changed how humanity thought about energy, light, matter, and ultimately, the universe itself. Planck had solved the Blackbody radiation problem, but in doing so, he had also revealed that the universe was far more mysterious than classical physics had ever allowed. The story of Planck's persistence continues into the years when his work began to intersect with the limitations of his era's scientific imagination. Even after deriving what would become Planck's law, he did not fully accept the radical implications of the constant he had introduced. He believed he was crafting a clever mathematical trick, a tool to force nature into giving up its secrets. But nature, as it often does, used Planck's own method to pull him deeper into mysteries he had never intended to enter. He worked tirelessly to refine his understanding, correcting errors, revising derivations, debating with colleagues, and running through endless mathematical pathways. Each attempt was a search for a classical explanation that could rescue his law from the strange idea he had used to construct it. Yet the more he refined his arguments, the more quantum behavior revealed itself as inevitable, not optional. His constant seemed to whisper its own truth. The universe is not continuous, but built from discrete packets, even if the world of the senses disguises this fact beneath the illusion of smoothness. Planck struggled internally, maintaining a life of external calm and discipline while privately wrestling with a scientific revelation that unsettled the very foundations of determinism. In his office, lined with books and quiet in its atmosphere, he tried for years to reframe his law without quantization, searching for a classical derivation that would allow him to remain loyal to the deterministic world, view he cherished. Many times he thought he had found a path that restored continuity, but each time the mathematics collapsed, revealing a contradiction he could not ignore. It was as if nature had constructed a puzzle with only one correct solution, and that solution required accepting energy as granular. He even turned to the thermodynamic principles he trusted deeply, hoping that by exploring entropy, irreversible processes, and statistical behavior, he might find a loophole. But instead, thermodynamics pushed him even further toward quantum thinking, as if the laws he respected most were conspiring to force him into a new intellectual domain he had never wished to enter. Meanwhile, the scientific community slowly began to absorb the implications of his formulas. Some dismissed them as contrived. Others regarded them as ingenious but incomplete. A few saw them as a gateway to something new. Planck read critiques with his usual patience, answering objections point by point, always respectful yet firm. At conferences, he presented his arguments with modesty, never overstating the significance of his findings, always careful to defend only what he believed he had logically proven. But even in his cautious tone, listeners could sense the weight of his discovery. Though he had not declared a revolution, the revolution had already begun its silent expansion from within his equations. Planck's constant began appearing everywhere, first in his own work, then in Einstein's analysis of the photoelectric effect, then in Bohr's atomic model, and soon throughout a new landscape of physics no one yet had the courage to map. Planck watched this with a mixture of pride and unease, respecting Einstein's brilliance while hesitating to follow his bold claims about light quanta. He admired the younger physicist, but remained reluctant to accept the idea that light itself could be particulate. This reluctance revealed Planck's nature. He was the reluctant founder of a theory more revolutionary than he wanted. He had always seen himself as a custodian of classical thought, someone who solved puzzles by refining existing ideas, not by destroying them. Yet destiny had assigned him a different role, and he fulfilled it with dignified responsibility even as he resisted some of its implications. This period of scientific upheaval coincided with profound personal turmoil. Tragedy entered Planck's life repeatedly, shaping the tone of his later reflections and deepening his sense of philosophical humility. His perseverance as a scientist was mirrored by an even stronger perseverance as a human being who suffered loss but continued forward. These emotional battles infused his work with a tempered wisdom. He came to believe that scientific truth, like life's meaning, emerges from the tension between certainty and mystery. The same mind that once sought absolute determinism now accepted, however reluctantly, a universe in which discontinuities and probabilities played a fundamental role. He never abandoned rationality, but he broadened it, allowing room for the unexpected and the unfamiliar. As the scientific world evolved around him, Planck became a mentor to a generation of young physicists who embraced quantum thinking with enthusiasm he never shared but always respected. They saw in his constant a doorway into a deeper understanding of nature, while he saw in it a challenge to centuries of philosophical commitments. Yet he supported their work, not because he agreed with everything they proposed, but because he valued truth above personal preference. He encouraged them to push the boundaries of physics, to test ideas rigorously, and to accept wherever the evidence might lead. His laboratory became a place where caution coexisted with innovation, a space where young minds such as Sommerfeld and others found both guidance and intellectual discipline. Through countless discussions, experiments, and arguments, the quantum idea matured. Planck witnessed its expansion into theories he would never have imagined, theories in which electrons leapt between discrete energy levels and light behaved sometimes as a wave and sometimes as a particle. He observed as Heisenberg formulated uncertainty and Schrödinger wrote equations describing quantum waves. The world he had entered reluctantly now stretched far beyond his original intentions. Yet he accepted its growth with grace, recognizing that science was not about preserving tradition, but about uncovering nature's laws, no matter how strange they appeared. Even as accolades accumulated and he received honors from around the world, Planck maintained a humble demeanor, never claiming to have overturned physics, only to have followed logic wherever it led. In speeches, he referred to his constant as a gift from nature rather than an invention, emphasizing that discoveries are moments in which the universe reveals a fragment of its structure to those willing to look deeply enough. He reminded younger scientists that humility is essential because no matter how much is learned, nature always retains more secrets than it reveals. His daily routine remained simple throughout his life, marked by disciplined work, music, philosophical reading, and long walks during which he reflected on the relationship between science, meaning, and human responsibility. These reflections shaped his belief that science and culture must coexist, that scientific discovery must remain connected to ethics, art, and the broader human experience. He insisted that physics was not a cold pursuit, but an expression of humanity's desire to understand its place in the cosmos. Later in life, as quantum mechanics became the foundation of 20th century technology, Planck recognized that the constant he had reluctantly introduced had transformed the world far beyond the confines of theory. It shaped electronics, chemistry, computation, and our understanding of the atom. It became a fundamental constant of nature, engraved into textbooks and experiments, measured with extraordinary precision, and used to define physical units themselves. Planck lived long enough to see his constant woven into the fabric of global scientific knowledge, a symbol of the universe's hidden granularity. He often spoke quietly about his journey, acknowledging its unexpected twists. He had not set out to change physics, yet he had done so by following a trail of logic that led him to a discovery no one could ignore. He had not intended to challenge determinism, yet his work opened the door to a world governed by probabilities. He had not sought fame, yet he became one of the most influential physicists in history. Through all this, he remained the same modest scholar who preferred clarity to noise, substance to spectacle, and truth to personal comfort. As the quantum revolution continued, Planck became a living bridge between two eras, the classical past he cherished and the quantum future he had initiated. Young physicists regarded him with reverence, not only for his scientific achievements, but also for his character. They saw in him a model of intellectual honesty, resilience, and moral stability. He bore witness to a transformation he did not fully embrace, but nevertheless helped to guide. His support provided the quantum generation with legitimacy and strength, ensuring that the new ideas grew on solid foundations rather than reckless enthusiasm. In the final years of his career, Planck reflected frequently on the nature of scientific progress. He observed that new ideas rarely triumph by convincing their opponents, but rather when a younger generation grows up already familiar with them. His law would become a cornerstone of that generational shift. He did not express bitterness toward those who resisted his constant. He understood their reluctance, for he had once shared it. Instead, he viewed scientific progress as an unfolding process in which each generation contributes pieces to an ever-expanding mosaic of understanding. The more he saw quantum mechanics flourish, the more he appreciated the interplay between human limitation and natural truth. He realized that the universe does not change because we prefer classical or quantum descriptions. It simply behaves according to its own rules, and humans must adjust their thinking to match reality. His constant became a symbol of this adjustment, a reminder that the universe often reveals its deepest truths through unexpected mathematical necessities rather than philosophical comfort. Throughout his later life, Planck continued to write, lecture, and guide younger scientists. His tone softened with age, becoming more reflective. He spoke of the beauty of natural laws, the harmony between mathematics and reality, and the importance of humility in the face of the unknown. He reminded audiences that science is an unending journey, one in which each discovery opens new questions. He believed that the constant bearing his name was not an endpoint but a beginning, a window into further mysteries yet to be uncovered. His presence at scientific gatherings brought a sense of continuity and stability, as if he were the quiet axis around which the evolving quantum world could revolve. Even when he disagreed with newer interpretations, he did so respectfully, valuing dialogue over confrontation. His role became that of a wise observer, someone who understood the weight of scientific revolutions not in terms of triumphs and defeats, but in terms of humanity's growing comprehension of nature. The story of Planck's persistence culminates in the realization that his greatest strength was not his mathematical brilliance or his experimental insight, but his unwavering commitment to truth. He followed evidence even when it led him into philosophical discomfort. He corrected his own models even when they overturned his cherished beliefs. He supported younger thinkers even when their ideas challenged his worldview. His constant became a monument not only to quantum physics, but to intellectual courage. Through personal loss, scientific upheaval, and societal turmoil, Planck maintained the conviction that truth, once discovered, must be embraced, regardless of how unsettling or unfamiliar it may be. His persistence was not the stubbornness of someone clinging to old ideas, but the perseverance of someone willing to pursue logical necessity even into regions of thought no one had previously mapped. His journey exemplifies the ideal of scientific integrity, to follow nature's clues with honesty, patience, and humility. By the time the world recognized the full implications of his work, Planck had already internalized them with a quiet sense of acceptance. He understood that the quantum world did not destroy the classical, but extended it, revealing subtler layers beneath phenomena once taken for granted. He saw that uncertainty, discontinuity, and probability were not enemies of order, but integral components of a deeper, more intricate structure. His constant became the bridge between the tangible world of everyday experience and the invisible realm of atomic processes. In this sense, the story of Planck's persistence is not merely a scientific tale, but a philosophical journey. It reflects the human struggle to reconcile intuition with evidence, tradition with innovation, and comfort with truth. Planck demonstrated that when the universe presents a new idea, even one as strange as quantization, humanity must rise to meet it. His perseverance ensured that physics did not shy away from this leap, but instead embraced it, opening a path that has shaped every aspect of modern science and technology. His legacy is therefore not confined to quantum theory alone. It lives in the spirit of inquiry that drives all scientific advancement. It reminds future generations that nature rewards those who pursue its secrets with patience and rigor. And it stands as a testament to the idea that even the most reluctant discoveries can transform the world when guided by honesty and determination. In the quiet resolve of Max Planck lies the origin of one of the greatest revolutions in human understanding, a revolution born not from ambition, but from the patient, persistent search for truth. The third keynote centers on Max Planck's profound belief in the unity and harmony of natural laws, a belief that guided both his scientific reasoning and his personal philosophy. Throughout his life, Planck saw nature not as a chaotic collection of unrelated events, but as an interconnected system governed by deep, elegant principles waiting to be uncovered. This conviction shaped his approach to physics long before the quantum idea emerged and remained at the core of his world. Even when quantum theory began to challenge centuries of classical assumptions, Planck believed that the universe possessed an underlying order, and that the task of science was not to impose structure, but to reveal the structure already present. His faith in this hidden harmony gave him the fortitude to confront problems that many of his contemporaries considered unsolvable, such as the Blackbody radiation puzzle that ultimately led him to introduce quantization. Even when this step contradicted his own philosophical preferences, he justified it through the same principle. Nature must be consistent, and if inconsistencies appear, it is the scientist's duty to resolve them, even if the resolution demands a radical reinterpretation of physical reality. Planck's search for unity in natural laws manifested in his methodical, almost meditative approach to research. While others leapt toward bold and speculative ideas, he advanced slowly and deliberately, ensuring that every conclusion was grounded in logic and mathematical necessity. His calculations were not merely technical exercises. They were expressions of a deeper belief that mathematics served as the language through which nature communicates its structure. When he derived the formula that would become Planck's law, he did so not by accident or intuition, but through an unwavering trust that thermodynamics, probability, and mathematics must converge upon a single coherent answer. That answer, once obtained, did not feel to him like a personal invention, but rather a revelation of nature's own logic. This humility, grounded in his conviction of universal harmony, prevented him from celebrating his discovery as a triumph, and instead allowed him to see it as one more step along the endless path toward understanding. Even as quantum theory expanded in directions he never intended, Planck continued to emphasize the unity of physical laws. While younger physicists embraced the probabilistic interpretations of quantum mechanics, Planck held onto the belief that a deeper deterministic foundation must exist beneath the apparent randomness of microscopic processes. He did not reject the new theory. He accepted its success, but insisted that its full meaning had not yet been grasped. For him, the quantum revolution was not the destruction of classical order, but the unveiling of a deeper, more subtle order. He believed that one day, the contradictions between classical determinism and quantum probability would be resolved in a synthesis that preserved the underlying coherence of nature. Though he did not live to see the development of quantum field theory or the Standard Model, his intuition that nature operates through unified principles proved prophetic. Planck's belief in unity extended beyond physics into his views on culture, ethics, and human responsibility. He saw science, art, and philosophy as complementary expressions of the human desire to understand the world. Music, in particular, played a central role in his life. He was an accomplished pianist and found in musical harmony a metaphor for the harmony he sought in physical laws. Music offered him emotional balance and strengthened his conviction that beauty and truth often arise from the same deep source. He frequently described natural laws as possessing an aesthetic elegance that paralleled the structure of a symphony, complex yet coherent, intricate yet unified. This perspective made him sensitive to the cultural shifts around him, especially during the turbulent political climate of early 20th century Germany. He believed that scientific progress depended on intellectual freedom, ethical integrity, and respect for universal principles that transcended national or political interests. In times of crisis, Planck's belief in unity gave him moral resilience. He endured personal tragedies, witnessed 2 world wars, and experienced the upheavals of a rapidly changing society. Through all of this, he held firmly to the idea that truth remains constant, even when human institutions falter. His speeches during these periods often emphasized the same themes: science as a pursuit of universal order, the responsibility of scholars to uphold ethical values, and the importance of preserving cultural and intellectual unity in the face of fragmentation. His steady voice provided reassurance to younger physicists who admired him not only for his scientific achievements, but also for his integrity and clarity of purpose. Ultimately, the third keynote captures the philosophical core of Max Planck's legacy. His scientific discoveries changed the world, but they were grounded in a world-view that valued harmony, unity, and the coherence of natural law above all else. Even when confronted with a theory as revolutionary as quantum mechanics, he held onto the belief that nature's underlying structure was rational and interconnected. This conviction guided his approach to science, shaped his interactions with colleagues, and sustained him through personal and societal challenges. Planck saw himself not as a disruptor, but as a seeker of truth, someone who followed the quiet logic of nature wherever it led. His belief in the unity of natural laws continues to inspire scientific inquiry today, reminding us that beneath the complexity of the universe lies a profound coherence waiting to be revealed. The fourth keynote revolves around a defining aspect of Max Planck's character: his profound intellectual humility and the quiet dignity with which he approached both science and life. Though he is now remembered as the father of quantum theory, Planck never carried the ego or triumphalism that often accompanies revolutionary discoveries. Instead, he maintained a calm, almost understated demeanor, as if he were merely a servant of truth rather than its master. This humility shaped every step of his scientific journey, especially in moments when his own work challenged established beliefs or contradicted his personal philosophical preferences. Planck never saw himself as a genius who reshaped the world. He saw himself as a patient observer trying to interpret nature's language as faithfully as possible. He believed that scientific breakthroughs were not personal victories, but glimpses of universal laws that existed long before humans learned to articulate them. This mindset allowed him to navigate the complexities of emerging quantum ideas without seeking glory, allowing the science itself, rather than his name, to command the spotlight. Planck's humility was particularly evident in the way he responded to the reception of quantum theory. When he introduced the concept of energy quanta in 1900, he did not claim to have discovered a revolutionary principle. In fact, he spent years trying to reconcile his own formula with classical physics, uncomfortable with the radical implications of the idea he had introduced. Instead of insisting that the world adopt his interpretation, he approached the matter with caution, acknowledging the limits of his own understanding. He openly stated that he had been forced to take an extreme step to make his calculations work, and encouraged others to explore the meaning of this step more deeply. This willingness to admit uncertainty distinguished him from many scientists of his era, who were often quick to defend their theories and reluctant to acknowledge any flaws. Planck's humility allowed the quantum idea to grow organically, inviting contributions from Einstein, Bohr, and later Heisenberg and Schrödinger, all of whom expanded the theory beyond what Planck had imagined. His humility also shaped the way he interacted with younger physicists. Though he was older and deeply rooted in the classical world, he never dismissed the ideas of the new generation. He listened carefully, debated respectfully, and regarded their insights with genuine curiosity. He may not have agreed with every interpretation, especially those involving probability and uncertainty, but he recognized the brilliance and potential of the emerging quantum framework. When Heisenberg introduced matrix mechanics and Schrödinger proposed wave mechanics, Planck did not resist the unfamiliar mathematics or criticize the abstract nature of the theories. Instead, he encouraged exploration, understanding that scientific progress depends on open-mindedness and the willingness to entertain even the most unexpected ideas. His humility made him a stabilizing presence during a time when physics was undergoing intellectual turbulence. He became a quiet guide, offering perspective without imposing authority. This humility took on an even deeper dimension in Planck's personal life, where he faced sorrows that would have broken many others. The losses he endured, his son Erwin in World War I, his daughters Gret and Emma, and later his son Karl, cast long shadows over his life. These tragedies never hardened him or pushed him toward bitterness. Instead, they deepened his sense of empathy and introspection. He continued to work, teach, and contribute to the scientific community, driven not by ambition, but by a steadfast belief in duty and purpose. His scientific humility was matched by emotional resilience, allowing him to face unimaginable pain with a quiet strength that inspired those around him. He understood that human control is limited, and he accepted uncertainty in life with the same philosophical calm he showed in science. Planck's humility extended beyond the personal and intellectual realms into the moral sphere. During the rise of political extremism in Germany, he tried to protect scientific institutions and colleagues while maintaining his integrity. Though he did not see himself as a political figure, he acted out of principle, guided by a belief in truth, freedom, and human dignity. He spoke carefully yet firmly when necessary, advocating for academic independence and the protection of persecuted scientists. Even when his efforts were unsuccessful, he persisted quietly, using whatever influence he had to preserve the foundations of scientific culture. What makes Planck's humility remarkable is that it was not weakness or self-doubt, but a deep confidence in the nature of truth. He believed that the universe was larger than any individual, and that a scientist's role was to serve knowledge rather than dominate it. This perspective kept him grounded even as he became a global icon, receiving awards, honors, and recognition from every corner of the scientific world. He accepted these honors gracefully, but never allowed them to distort his sense of self. He often said that he stood on the shoulders of giants, and that any achievements of his own were part of a continuum of human inquiry. This humility shaped his final reflections on science. He saw physics as a journey without end, in which each answer leads to new questions, and each discovery deepens the mystery rather than resolving it completely. He believed that intellectual modesty was essential because nature always has more to reveal. Planck's humility became, in its own way, a guiding principle for the generations that followed him. It reminds us that genuine breakthroughs come not from arrogance, but from attentiveness, patience, and the willingness to accept truths that challenge our deepest assumptions. His life demonstrates that greatness does not require loud declarations or dramatic gestures. Sometimes it is expressed in quiet persistence, unwavering integrity, and the courage to follow truth wherever it leads, even when it leads into the unknown. Through this humility, Max Planck not only transformed physics, but also offered a model of scientific character that remains as powerful and relevant today as his constant. The fifth keynote reflects Max Planck's deep conviction that scientific truth is not shaped by public opinion, popularity, or the approval of contemporaries, but by the quiet and relentless force of evidence. This principle guided his philosophy of science and became a defining part of his legacy. Planck knew that new ideas rarely win because their opponents suddenly recognize their correctness. Instead, they prevail because a new generation grows up familiar with them, with minds unburdened by old assumptions. Planck expressed this idea in one of his most quoted reflections, that scientific progress happens one funeral at a time, not through persuasion, but through replacement. Although this line is often interpreted cynically, for Planck it was more an observation about human nature than a complaint. He recognized that deeply rooted ideas shape how people see the world, and that even the most brilliant scientists struggle to abandon frameworks they have trusted for decades. He himself had experienced this conflict when his own discovery challenged the classical world, he cherished. What made Planck exceptional was that he acknowledged this struggle within himself just as clearly as he saw it in others. Planck's experiences during the birth of quantum theory confirmed this belief repeatedly. When he introduced the idea of energy quanta, many physicists resisted it, not necessarily because the mathematics was flawed, but because they could not imagine a universe in which energy came in discrete packets. The assumption of continuity had been so deeply woven into the fabric of classical physics that even considering alternatives felt almost unthinkable. Planck understood their hesitation, for he felt it internally as well. Yet he observed that young physicists, those who had not grown up steeped in 19th-century determinism, embraced the quantum idea more readily. To them, quantization was not a threat but an opportunity, a chance to explore new theoretical landscapes that the older generation preferred not to enter. This difference between generations fascinated Planck. He saw in it a natural pattern of intellectual evolution, one that ensured science would always move forward even when individuals preferred to stay rooted in tradition. His belief that truth advances generationally influenced the way he taught and mentored young physicists. Instead of demanding adherence to classical thinking, he encouraged his students to develop their own perspectives. He welcomed the boldness of minds like Einstein and Bohr, praising their creativity even when he disagreed with their interpretations. Planck understood that the future of physics belonged to those willing to push boundaries, and he saw his role not as a gatekeeper, but as a stabilizing presence who could help guide the transition from old ideas to new ones. He valued dialogue and intellectual freedom, believing that a healthy scientific culture required space for dissent, debate, and the exploration of unconventional ideas. His recognition of generational change allowed him to let go of control, giving younger scientists the confidence to develop theories that would reshape the world. This keynote also reflects Planck's broader understanding of human psychology. He recognized that beliefs, once formed, become intertwined with professional identity, emotional security, and intellectual pride. Changing one's beliefs is not simply a matter of logic. It often requires a reorganization of one's worldview. Planck knew this because he had lived through it himself. He had loved classical physics, admired its elegance, and trusted its principles. Yet his own work forced him to confront evidence that contradicted its assumptions. He did not abandon classical physics lightly, nor did he embrace quantum theory quickly. It took years of reflection, revision, and reluctant acceptance before he acknowledged that nature had revealed something fundamentally new. This personal experience made him empathetic toward the hesitation of others. He understood that acceptance takes time and that sometimes only a new generation raised with different assumptions can fully embrace paradigm shifts. Planck's belief in generational progress was not pessimistic, but quietly hopeful. It reassured him that humanity's pursuit of truth would continue even when individuals resisted change. He believed that truth has a longer lifespan than any human, and that it ultimately carves its own path through the collective mind of society. This faith in truth gave Planck the patience to endure criticism, indifference, and skepticism during the early years of quantum theory. He did not feel threatened by resistance. He saw it as an inevitable stage in science's long journey. This perspective allowed him to remain calm amid controversy, secure in the knowledge that if his ideas were correct, time itself would become their greatest advocate. Beyond physics, Planck saw this principle reflected in cultural and social change as well. He believed that moral and intellectual progress often faced similar resistance, with each generation inheriting and then reshaping the values of its predecessors. His experiences during turbulent political eras reinforced this view. He recognized that societies evolve not through sudden enlightenment, but through gradual shifts in thinking, as younger voices rise to prominence and older frameworks fade. His reflections on science became reflections on humanity, shaped by decades of personal loss, public upheaval, and intellectual transformation. In the end, this keynote captures Planck's profound understanding of how ideas spread, mature, and eventually take hold. He saw scientific progress as a living process, one that unfolds across lifetimes rather than moments. It is a reminder that great ideas do not win by force, but by endurance, growing quietly until the world is ready to recognize them. Planck's perspective encourages patience, humility, and trust in the long arc of truth. Even as he became a central figure in one of the greatest scientific revolutions in history, he remained aware that his role was only one part of a much larger story, one in which each generation contributes to the shaping of human understanding. The sixth keynote highlights Max Planck's remarkable dedication to the rigorous application of mathematics as the language through which nature reveals its deepest truths. Planck believed that mathematics was not merely a tool for describing physical phenomena, but the very framework by which the universe itself operates. From his earliest studies to his groundbreaking work on Blackbody radiation, he consistently sought precision and clarity in mathematical formulation. For him, equations were not abstractions. They were expressions of reality, windows into the underlying order of nature. Every symbol, every relationship, every constant carried meaning far beyond its immediate calculation. He approached each problem with meticulous care, ensuring that the logical structure of his arguments was flawless, and that every step reflected the constraints imposed by both experiment and principle. This commitment to mathematical rigor became the foundation for his revolutionary discoveries and distinguished him from many of his contemporaries. When confronted with the challenge of Blackbody radiation, Planck relied on his mathematical insight to navigate the seemingly insurmountable obstacles posed by classical physics. Classical theories failed spectacularly at predicting the observed spectrum, especially at short wavelengths, producing what became known as the ultraviolet catastrophe. While others attempted empirical adjustments or relied on incomplete approximations, Planck sought a derivation grounded in first principles. He combined thermodynamics, statistical mechanics, and electromagnetic theory, weaving them into a coherent mathematical framework. It was this insistence on rigor that allowed him to uncover a solution where others had faltered. He did not settle for partial explanations or formulas that only worked under limited conditions. He demanded a derivation that could stand the scrutiny of both mathematics and experiment across the entire spectrum of radiation. In doing so, he introduced the idea that energy exchanges occur in discrete packets, a subtle yet profound innovation encoded within the mathematics itself. Planck's approach reflected a belief that nature is inherently logical, and that inconsistencies in theory signal incomplete understanding rather than flaws in the natural world. He treated mathematics as a mirror of reality, capable of revealing truths invisible to intuition alone. When his derivation of the Blackbody spectrum required the introduction of what would become Planck's constant, he recognized that the mathematics demanded it, even if its physical meaning was initially unclear. The constant was not a whimsical invention, but a necessity revealed by rigorous analysis. To Planck, this was evidence that the universe communicates through the structures mathematics provides. To ignore such indications would be to deny the voice of nature itself. Beyond problem-solving, Planck's dedication to mathematical precision shaped the way he communicated ideas and mentored younger physicists. He believed that clarity in expression and careful formulation of equations were essential for intellectual progress. A poorly expressed theory, no matter how innovative, could mislead, confuse, or slow the advancement of science. He encouraged colleagues and students to pursue elegance in derivation and consistency in reasoning, fostering a culture of disciplined inquiry. This approach not only ensured the robustness of quantum theory in its formative years, but also established a standard for scientific rigor that continues to influence physics today. His insistence on precision extended to experimental validation, where he treated data with the same careful attention as his equations, understanding that the interplay between theory and experiment was the ultimate test of truth. Planck's reliance on mathematics also shaped his philosophical outlook on the natural world. He viewed the universe as governed by universal laws, discoverable through careful reasoning and analysis. He did not believe in arbitrary phenomena or capricious events at the fundamental level. Instead, he saw patterns and structures waiting to be articulated through logical relationships. This belief underpinned his perseverance even when confronting revolutionary ideas like energy quantization, which seemed counterintuitive and challenged centuries of classical thinking. The mathematical necessity of discrete energy levels compelled him to accept a reality that intuition alone might reject, demonstrating the power of mathematics to guide understanding beyond what the senses or preconceptions could perceive. Planck's dedication to rigor extended into his broader understanding of science as a discipline. He saw physics not as a collection of facts, but as a coherent system built upon principles that can be expressed, tested, and refined mathematically. He respected those who approached the subject with the same discipline, and he recognized that breakthroughs, even radical ones, gain legitimacy through careful formulation. Quantum theory, for all its strangeness, succeeded in large part because Planck's meticulous mathematics provided a solid foundation upon which others could build. Without such precision, later developments by Einstein, Bohr, and Heisenberg might have remained speculative rather than transformative. In the end, this keynote illustrates that Planck's mathematical rigor was not a mere habit or preference, but the very lens through which he engaged with reality. His approach demonstrates that true scientific discovery requires patience, discipline, and fidelity to the internal logic of nature as expressed through equations. By insisting that every derivation, every constant, and every assumption and rigorous scrutiny, Planck ensured that the quantum ideas he introduced would endure and expand, providing a reliable foundation for the extraordinary developments that followed. His work shows that the path to understanding the universe is not paved by intuition alone, but by the precise and careful language of mathematics, through which the hidden structures of reality are revealed and preserved for generations to come. The seventh keynote emphasizes Max Planck's enduring influence on the scientific community and the legacy he left not only through his discoveries, but through the principles and values he instilled in generations of physicists. Planck understood that the work of a single individual, no matter how groundbreaking, gains significance only when it contributes to a larger, evolving conversation. He approached his career not as a pursuit of personal glory, but as a dedication to advancing human understanding of the natural world. His achievements, most notably the introduction of energy quanta, became a foundation upon which an entire century of scientific innovation was built. Yet even as he shaped the course of physics, he remained aware that discoveries themselves are transient. It is the intellectual culture, the method of inquiry, and the ethical standards of community that endure. This awareness informed his interactions with colleagues, his mentorship of younger scientists, and his efforts to protect and strengthen scientific institutions throughout his life. Planck's influence on the scientific community was amplified by his ability to combine visionary insight with steadfast responsibility. Unlike some pioneers whose radical ideas alienated their contemporaries, Planck maintained credibility and trust through his measured approach. He presented revolutionary concepts carefully, ensuring they were supported by rigorous mathematics and experimental evidence. This careful balance between innovation and rigor made his ideas both persuasive and enduring. Scientists who followed him could build upon his work with confidence, knowing that it was grounded in logic and disciplined analysis. His example demonstrated that revolutionary discoveries do not need to discard the values of precision, patience, and humility. Instead, these values can guide even the most transformative breakthroughs. Beyond the technical contributions, Planck shaped the culture of physics by embodying integrity, patience, and ethical responsibility. He understood that science flourishes when debate is respectful, inquiry is disciplined, and ideas are tested rigorously. He encouraged open discussion and critical thinking, fostering a community in which young physicists could explore bold concepts without fear of ridicule or suppression. Planck's mentorship was subtle yet profound. He offered guidance, supported the work of younger colleagues, and provided an intellectual foundation for the rapidly emerging field of quantum mechanics. Figures such as Einstein, Bohr, Heisenberg, and Schrödinger operated in a world shaped by Planck's careful introduction of quantum ideas and his insistence on rigorous reasoning. His influence extended beyond formulas and constants. It was embedded in the ethos of scientific inquiry he cultivated. Planck's commitment to the integrity of science also manifested in his dedication to protecting institutions and colleagues during periods of societal upheaval. He witnessed the turbulence of early 20th century Europe, including wars and political extremism, yet remained committed to the principle that scientific pursuit must remain independent and ethical. He advocated for the protection of scholars, the freedom of research, and the preservation of knowledge even in the face of adversity. By doing so, he ensured that physics could continue to evolve unimpeded, and that new ideas could flourish in a stable and principled environment. His legacy is as much about creating a culture in which science could grow responsibly as it is about the equations he derived. The generational impact of Planck's work is particularly striking. He understood that scientific revolutions are rarely immediate. They take root slowly, often through the education and development of younger scientists who inherit the seeds of new ideas. By fostering intellectual curiosity and emphasizing rigorous methodology, he helped shape the minds that would extend quantum theory far beyond its initial formulation. He appreciated that while his own contributions were pivotal, the long-term success of science depended on the cultivation of a community capable of exploring, challenging, and refining these ideas. In this sense, his influence is ongoing, reverberating through the structure of modern physics and beyond. Planck's life also demonstrated the intertwining of scientific and humanistic values. He balanced the pursuit of knowledge with a recognition of the broader responsibilities of scholars, emphasizing ethics, cultural awareness, and the necessity of humility before nature. He believed that discoveries carry obligations to truth, to society, and to future generations. His example encouraged scientists to see themselves not merely as collectors of facts, but as stewards of understanding, responsible for ensuring that knowledge serves humanity and respects integrity of inquiry. The legacy he left is therefore multidimensional. It encompasses both the mathematical insights that underlie quantum mechanics and the ethical, philosophical, and cultural framework within which scientific progress should occur. Ultimately, this keynote illustrates that Max Planck's influence extends far beyond the discovery of energy quanta. He shaped a scientific culture that values rigor, integrity, mentorship, and ethical responsibility. He demonstrated that transformative ideas gain lasting impact when they are presented with precision, defended with humility, and nurtured through collaboration. His example reminds us that the progress of science is not only a matter of formulas and experiments, but of cultivating a community capable of sustaining inquiry, questioning assumptions, and embracing truth wherever it leads. In this way, Planck's legacy endures not just in the constants and equations that bear his name, but in the living, evolving spirit of the scientific enterprise itself, which continues to explore the universe with the rigor, patience, and insight that he so exemplified.